Hello everyone, welcome to lecture 5 of our course. Today we will be exploring an exciting generative artificial intelligence topic, the generative diffusion model with its applications. I'm Hongyang, an assistant professor from the Department of EEE, the University of Hong Kong. Before we begin our discussion, I want to emphasize that today's lecture we will cover both the AI foundations and also the knowledge from the wireless communication networks, making it relevant to both the academic foundations and also the practical implementation. Okay, let's start our exploration. Here is today's agenda. We will cover 4 parts. The first part is about the background of diffusion model. In this part, we will introduce the mathematical foundation behind the diffusion model. And then we will go with the network system for diffusion model. We will explain how the communication networks can support the diffusion model, including the model training, fine-tuning, and the inference process. Third, we will discuss the role of diffusion model in the communication networking systems. We will discuss how the diffusion model can be used in the networking system design and also the communication network optimization. And finally, we will end this lecture with a brief summary. For the background part, we can start by understanding the generative artificial intelligence, GenAI. Generative AI is a branch of artificial intelligence that uses generative models to produce text, image, video, or other different kinds of data. From these slides, we can see many familiar examples. For example, in the area of text generation, we have ChatGPT and Google's BERT, and also we can see the partnership between OpenAI and Microsoft, which has transformed the Microsoft Office applications. Also, in the area of image generation, we have Midjourney and Stable Diffusion. The users can just upload a textual prompt, then the model can generate the image according to the textual prompt. As we can see, in the area of language generation, the transformer plays an important role like the GPT. But in the area of image generation, the diffusion model is very important. Moreover, in the area of video generation, we have Sora, which is a very famous application developed by the OpenAI company. Sora is also a diffusion model-based AI application that can generate the video according to the text description from the users. You may wonder why diffusion model is chosen by these big companies, and what's the mathematical theory behind the diffusion model that makes it unique. This slide shows the historical development of diffusion model. In fact, when the concept of diffusion is first proposed, it's different from what we are using today. In the earlier approach of diffusion model, we use the score matching to train the energy-based model. Then we use the Langevin equation to sample from the model. This is the direct idea, but when the data emission is very high, the performance is not that good. This makes the previous design of diffusion model cannot handle the high-resolution image generation. The breakthrough came with the DDPM, Denoising Diffusion Probabilistic Model. Here is the pumpkin image. We use this as an example to see how DDPM works. From this example, we can see for the DDPM, there are 2 different processes. The first one is about the forward diffusion process. In this process, we gradually add noise in the original image and finally get the Gaussian noise. And in the backward denoising process, we train the neural network by denoise the noised version. We can see from this example to understand this process. We have many different kinds of tools, and if we increase the temperature, we can increase the entropy, and finally make these tools to the molten iron. If we want to make tools directly from the molten iron, it's very difficult. But in fact, we can learn the steps of the making tools process. Going deeper, don't worry if you feel these equations are very complicated. We can understand it in a simple way. At the top is the denoising chain we just mentioned. X0 is like the pumpkin image, and XT is the Gaussian noise. So for the forward process, we will gradually add noise. As shown in this equation, we can see there are two important parameters. The first one is called alpha. We can use this parameter to control to what extent the original image can be kept. And another parameter is called beta. So this parameter controls how much noise we add in this step. And after some mathematical derivation, we can get the relationship between x0, the original image, and xt, the noised version at the step t. So this is like the forward diffusion process. And for the denoising process, what we want to do is to train a model to denoise the noised image and get the original image. This is also called the generation process. So for the model, the input is the noised version, xt, and what we want to minimize is the loss between xt-1 and the output of the model. So in fact, what we want to do is let the model can denoise the gap between two steps by predicting the noise we add in this kind of two different states. So because we have the relationship between xt-1 and xt, after some mathematical derivation, we can get the loss function used in the DDPM paper. Because of the diffusion model, it has a strong learning ability, a good performance, and it's very easy to be trained. Now the diffusion model has been used in many different kind of areas. For example, in the computer vision area, it's used for generate many different kind of images. And also in the text generation, audio generation, and even for the medical image generation. But from a telecommunication perspective, what we care is about the role of diffusion model in networking systems. So we have two separate questions. The first question is about we use network for the design of diffusion model. For example, how can we use networks to support different kinds of generative diffusion model training and inference? Another question is about the role of diffusion model in networks. The question is how generative diffusion model can be used to improve the communication network performance. So let's move to the second part. We consider the network system for diffusion model. In this part, we will give two examples. The first one is about the training and fine-tuning. The second one is the distributed inference of diffusion model. If we use the networks to help for the distributed training of diffusion model, there are several advantages. The first one is about the user privacy. If we use the networking technology like the federated learning in the model training, we can protect the user privacy. Because like if we do the model training in a central way, we have to collect the dataset first. But some users, they don't want to share their data with the company. For example, if I have a hospital, there are many data related to the patients. I don't want to let this kind of information be released to the big company. So the second advantage is that the FL method can increase the data diversity. So this is like what we explained in the first point. Because there are some users, they don't want to share the data. But if they can do the local training, they can contribute this part of data information to the global model. So this is the second advantage. The third advantage is about enabling the participation of resource-constrained devices. As we know, many pre-trained models, they have tons of parameters and the model size is really large. But if we use the knowledge like split learning, we can let the devices to choose different size parts of the model in the training process. In this case, more and more devices can join the training process, and we can use the computing power in the resource-constrained devices. So the last advantage is about the personalization. If I have some local data and my own dataset, I want to train a personalized model. With the help of networking, I can do it in my local devices and achieve a higher user quality of service. So in the following, we will give some different structures of the federated learning-aided diffusion model training. So the first structure is the parallel approach. So in this approach, the central server will initialize the global model first. Then the model will be transmitted to the clients, the user side. Then at the user side, we can do the local model training and then upload the model to the central server. After several rounds of this kind of training, the central server can get the global model and share it with all the users. The second approach is called the split approach. Because like in the first way, the parallel approach, we can see the model must be transmitted from the server to the user and from the user to the server. So it will cost a lot of communication resources. But if, in fact, because some of the diffusion models, the parameters are very huge and the model size is large, it's difficult to transmit the whole model in every interaction. So we can use the split approach. In this approach, the server will split the model first, like we have the user side and also the server side. And also the server side will be kept in the server side. It will not be transmitted to the edge devices. And in this way, we can do the parameter updating and also share the gradients among different devices. And still, we can get the global model. The last method is called the sequential approach. So the aforementioned two approaches, we have a central server to control all the devices. But in this way, we can leverage the device-to-device communication among these kind of edge devices. For example, the Internet of Vehicles or the UAV swarm, we can let the devices to perform the D2D communication. And in this case, all the data of the edge devices can be used in the model updating. This slide shows an example of our mentioned network-aided diffusion model fine-tuning. Like the user wants to generate an image in the style of Chinese painting, but the global model can generate the colorful style image like this. In this case, the model or the user side can use their own data to do the fine-tuning. And we can see the loss function can be dropped, and also the performance is quite good. The generated image is in the Chinese painting style. Then the next point is about the distributed inference of diffusion model. This figure shows the image generation process, which is also called the denoising process, as we just mentioned. Here we give two different examples. The first one is a lemon on the table, and the second prompt is an apple on the table. So this is like people working in AI will consider the image generation process. But from a networking perspective, this kind of design is not optimal. Because we can see for different images, the generation starting point are same, the Gaussian noise. So we can consider a real example. Like we are at the airport and we want to build two different routes to two different destinations. So in this case, if we build the routes separately, we have to construct about 21 kilometers. But in fact, A better way is like we extend the road to a direction first and then branch off to two different destinations. And in this case, in total, we only need to construct 15 kilometers. If we bring this idea to the image generation, we can also reconsider the inference process of the image generation. So from this figure, we can consider the image generation process from the semantic perspective. So at the starting point, we have Gaussian noise. In this point, the semantic certainty is at its lowest. And with the denoising process, and finally we get the fixed image, and the semantic is also fixed. But in the middle point, in fact, at this point, we can change the prompt of different denoising passes, and finally get different images. We can have a look at the first three passes first. So in this case, for the pass 1, we have the prompt 1, a lemon on the table, and we can generate this image. But for the pass 2, we change the prompt from an apple on the table to a lemon on the table, and still we can get the image what we want. And for the pass 3, it's an apple on the table. But in this case, if we use pass 2 and pass 3 work together, the total energy cost is lower than we generate the image separately. So we can also think by considering the pass 4 to pass 6. So in this case, for example, at pass 4, we change the prompt from an apple on the table to a river in the forest. Because these two prompts, the semantic information is very different. So in this case, we cannot generate the image successfully according to the new prompt. But if we move the changing point from step 5 to step 2, we can generate the image successfully. So from this example, we can summarize some insights. If we want to change if we want to use this kind of design to save the networking resource cost, we should first gather the prompt according to their semantic information. If two prompts have a similar semantic information, we can generate these two images in a collaborative way. But if the semantic information is very different, in this case, if we want to let them work together, we have to change the point to a relatively early stage. So following this idea, we can design different kind of networking systems. For example, the H2 multiple devices. We can do the central denoising steps in the central server, and then share the intermediate results to two different kinds of devices, and let the H devices to perform the following denoising steps. And also, we can let two devices to work together to communicate with each other and share the denoising results. And also, we can form a cluster based on the semantic information of user prompts and let these kind of H devices to work together. We can give an example according to the first structure, the H server to user devices. So in this example, we consider that the users want to generate different images, and the server will help to perform some shared denoising steps, and then the intermediate output is transmitted to two different kind of users. As we can see, the denoising step will cost some computing resources, and also in the wireless communication part, we have to cost the communication resources. Therefore, our goal is to maximize the quality of experience of all the key users, but we have to decide the computing power, computing energy cost, and the communication energy cost. Specifically, for the computing side, we have the denoising steps in the central server and the key different user devices. And for the communication part, we have to decide the transmit power to different users. So this figure shows the relationship between the denoising steps and the energy cost. As we can see, if we increase the denoising steps, it will cost our much more the computing energy. And in this problem, we have to consider 3 different kind of constraints. The first constraint is about the computing energy limitation in user devices. The second constraint is that the AI-generated content service should meet the user's minimal quality of experience requirements. And TH is like the threshold. The last constraint is the energy constraint in the central server. The central server has to perform the wireless communication, like the intermediate image transmission, and also T0 steps of the denoising process. To solve this optimization problem, we can use different kind of approaches. For example, the reinforcement learning. And in this slide, we show the numerical results of the image generation. And here, we consider in the central server, we perform different steps of the shared denoising steps. And also in the user devices, there are several denoising steps. And we can see the generated image have different style. So because the user may have different preference, so we have to decide about the denoising steps in the server and the user devices. And also we can see if the transmit power is different, the bit error will also be different. So there is a trade-off between the energy we put in the communication and computing. If more energy is put in the communication part, we have to reduce the steps of the denoising process. In this case, the image quality may be reduced. But if we put more resource in the computing part, the communication power is not large enough. In this case, the bit error probability will be increased. Okay, next, we can move to the third point, diffusion model for network system. So in this part, we will also consider 2 representative examples. The first one is about diffusion model aided network system design. The second point is we use diffusion model in the network optimization. So for the first part, we can use the semantic communication as an example. First, let's introduce the semantic information briefly. In conventional communication, we want to transmit the source image from the sender to the receiver. But in semantic communication, what we want to do is to extract the semantic information from the sender, and we only transmit the semantic information instead of the original images to the receiver. And in this case, if the receiver side can achieve its tasks, we can say the communication process is successful. But a challenge in semantic communication is that joint training and the distributing of the semantic encoders and decoders is very complex and energy demand. But if we don't do the joint training at the receiver, the generated image, the information could be different. With the help of diffusion model, if we let the diffusion model act as the decoder in the receiver side, we can generate the image according to the textual prompt. And the textual prompt can be regarded as the semantic information of the original information. But in this case, if we didn't do any controlling, the generated image could be very different from the transmitted image. So in this case, this kind of design cannot be used when we want to transmit the source image in a precise way. For example, the images about the human face. So in this paper, we want to propose a new method that we transmit both the textual and the visual prompts as the semantic information. And with the help of diffusion model, if we can control the denoising chain, we can generate the image according to the input. So in this slide, we use the DDIM structure, the denoising diffusion implicit model. This is different with the DDPM we just mentioned. In DDIM, there is a parameter which can control the certainty or the uncertainty of the denoising chain. If we set this parameter at 0, we can fix the denoising chain. So in this case, if we use the xt as the semantic information, we can control the generated image. So the encoding process is like the forward diffusion process, and the decoding process is the denoising process. With the help of this kind of mathematical characteristics, we can design a semantic communication with the help of diffusion model. And here is the transmitter, and here is the receiver. After we do the semantic encoding, we can transmit the visual prompt and the text description to the receiver. And in the receiver side, with the help of diffusion model, we can generate the fixed image. And this slide shows the numerical result of our design. As we can see, whether it's an image about the nature or human face, we can get the image in a quite precise way. But another point we have to mention is about the diffusion steps. As we can see, if we increase the diffusion steps, the image quality can be increased. The reason is that although in the wireless transmission process, some bit error will happen in the transmitted information, but the generation process can recover the image according to the visual and the textual prompt it received. So in this case, we want to set a relatively higher diffusion steps, but it will also cost higher computing resources. So there is still a trade-off between the communication and the computing part. For the last point, we want to introduce the diffusion model-aided network optimization. So it's different with we just use the diffusion model as part of the AI-aided decoder or encoder. In this part, we will introduce how can we use diffusion model as an optimization tool in the network. So this part shows some papers about the diffusion model and the reinforcement learning. As we know, the reinforcement learning has been used in the communication for a long time. But with the help of diffusion model, the performance of reinforcement learning algorithms can be improved. This is because the ability of diffusion model, it can handle different kind of complex data distributions, like the environment in the reinforcement learning algorithm. And also it's very flexible because the ability of diffusion model to model diverse behaviors is useful in reinforcement learning. The agent can adapt to different kind of situations and user requirements. And the last point is about the planning capability of diffusion model. In this case, the diffusion model can be used for planning by iteratively denoising the trajectories. This is also very useful for the decision-making process in the reinforcement learning. So motivated by these advantages, we want to use the diffusion model to generate the network solutions. As shown in this figure, in the communication networks, we can observe different kind of like the channel conditions, the user requirements, and the system settings. We can see these are the environment we have. And the denoising process is like we want to generate the network solution which is optimal in this environment. So to do this, first we need to design the neural network like the denoising network. Here we use a simple MLP as the neural network for the denoising process. And after several steps of denoising, we can generate the optimal decision. But in communication networks, there are different situations. For example, sometimes we have the expert dataset. If we have the expert dataset, the dataset can be used like the image. We can add noise to the expert dataset and denoising it to let the neural network to learn the optimal solution. But if we don't have the expert, we have to redesign the loss function of the diffusion model. We can have a look at the first situation when the expert dataset is available. So in this case, if we want to use the diffusion model to generate the network solutions, there are several steps. The first step is to observe the current wireless environment. Then we find the expert solutions. For example, if the current wireless environment is like the channel state or the user requirement, and we already use some mathematical way, or we do the collection to get the optimal solution, we can use this optimal solution as the expert solution. And in this case, we can first add noise in the expert solution. It's like the forward diffusion process. And after we got the noise version, we can try to train the model according to the denoising process. And the loss function is designed to predict the noise we add in this step. For example, we can give a randomly selected time step t, and we do the forward process. And the input will be given to the neural network, and we can see the predicted noise is different with the added noise or is similar. And after several rounds of training, we can let the model to generate the network solutions. This is very useful, like for the wireless sensing scenario, because we will collect a large amount of data set. And this data set already contains the information what we want to use. And also, this is useful when we want to do the data set enhancement. For example, in wireless sensing, there are different kind of tasks. If we want to consider the tasks like trajectory or about the people running or walking, this kind of motion detection, it's very easy to collect the dataset. But there are also some cases it's not that easy to collect the wireless sensing dataset. For example, if we want to detect where people is falling down, it's difficult to do the experiment. So in this case, we can just collect a small amount of data and let the diffusion model to learn the pattern behind this kind of data set. And then the diffusion model can be used to generate more data samples, which can be used for the download the different tasks. So in the second case, we can consider a different scenario, which is the expert dataset is unavailable. So in this case, we don't have the expert dataset. For example, if we want to design the optimal power allocation schedule or the computing power allocation schedule, we don't have the dataset. So we have to let the diffusion model itself to explore what's the optimal solution. In this case, the training schedule is totally different with the first case, and totally different with the image generation, because we cannot add noise to an image or to an expert solution. And in this case, when the expert dataset is unavailable, what we want to do is to generate an action. It's like the generator solution can achieve the highest performance. And in this case, we will consider the training process from a reinforcement learning perspective. So the first step is still observe the current wireless environment, because the observed conditions will act like the textual prompt we input to the denoising network. And in this case, we just input the observed condition to the denoising network and let the network to generate a solution. In this case, the generated solution may not be optimal, but we can perform this kind of network solution in the environment and get the feedback. And the loss function is redesigned to maximize the feedback. So after several rounds of interaction with the environment, we can let the denoising network learn to generate the best network solutions that can achieve the highest performance metrics. So the performance metric can act like the reward in the reinforcement learning, and the prompt is like the observed state of the reinforcement learning. And in this case, even the expert dataset is unavailable, we can still get a denoising network to generate the optimal solutions. So in the following, we will give a simple example to explain our ideas. And in this case, we consider a very simple power allocation problem. And there are m different wireless channels, and each channel have a different channel gain. And what we want to do is try to design the power allocation schedule can achieve the highest data rate. First, let's take a look at this problem. It's not very difficult to be solved. We can use like the water feeding algorithm or some reinforcement learning based algorithm to get the optimal power allocation. But this kind of algorithm can be also the resource cost can be also very high because it will involve some interactive process. And also, this problem is very flexible, and because the wireless environment is changing at any time. As we can see, there are three different figures, and each figure is about one set of the channel gains. And as we can see, if the channel gains are different, the optimal solutions are different. And also for a fixed environment, if we set the power to different values, the obtained channel rate will also be different. So what we want to do is to let the diffusion model to learn the environment. And finally, we can just input some observed information. And the denoising network will use our input as a prompt, as a condition to generate the optimal power allocation schedule. So use the framework we just mentioned. In this case, we don't have an expert, so we just let the denoising network to interact with the environment. And after several rounds of the training approach, we can get the loss functions as shown here. Here, the y value means the gap between the achieved data rate and the optimal data rate. So 0 means like it's exactly the optimal power allocation, and we've achieved the highest data rate. On the left-hand side, we can see the diffusion model on the different learning rate. We can achieve the near zero performance, but if the learning rate is different, the carrying speed is also different. So in this case, we have to set a suitable learning rate for the diffusion model. This figure shows like the compare between diffusion model and the reinforcement learning algorithms. As we can see, if we use the soft actor critic algorithm or the PPO algorithm, we can also achieve a quite good performance. But the diffusion model can achieve the highest converged speed. So in this figure, we consider different denoising steps in the diffusion model. As we just mentioned, in this case, we will perform a denoising chain, and after the backward denoising process, we generate the network solution. So if we set a different denoising step, we can achieve different network performance. Because like in the image generation, typically we can set a relatively higher number of steps. For example, if we want to generate an image, we can set it as 30 or 40 and get the generated image according to our textual description. But in the diffusion model, it's different. If we set the denoising step in a relatively higher number, the converged speed is not that high. The reason is that after several rounds of denoising, the performance the algorithm may be in the local optimal solutions, and it will take a longer time to achieve a higher performance. But if we set the denoising step relatively low, like if we set it only 3, the performance is also not that good, because in this case, the model cannot generate a fixed network solution, because it will generate the solution from the Gaussian noise and using the network condition as the prompt. In this case, we can set a relatively suitable step like 6 or 7. For this problem, the performance is quite good and stable. In this figure, we consider the cases that we have the expert dataset. Like for a given channel conditions, we know what's the optimal power allocation schedule. And in this case, the diffusion model can be trained in the way like we just mentioned. We can add noise to the expert solutions, and we learn the pattern from the denoising process. And we can see the performance is quite good. But we can also train the diffusion model without the expert solution. And we can see it will take a longer time to convert, and the performance is not that good with the cases with the expert dataset. In this slide, we consider a complex scenario that we have 70 different channels with different channel gains. And this figure shows the optimal power allocation schedules. And after we train the diffusion model, we can do the inference process. And after several steps of the denoising process, we can generate the real network solution we performed in the environment. As we can see, the output of the diffusion model is very similar to the optimal setting. This shows that the diffusion model can understand the environment and generate the solution according to the various environment. From the following discussion, from that simple example, we can understand the workflow of the diffusion model in the network optimization. And next, we can move to a more practical and complex problems of the network systems. So in this example, we consider the service provider selection problem. Specifically, we have many users which may have different requirements. For example, the image generation. So for user 1, he may want to generate an image about the city walk, and for user 2, he may want to generate an image of the animals like cats and dogs. So in the setting of their image generation, they may require different computing resources. For example, the steps of the denoising chain. If the user wants to generate an image with a higher number of denoising steps, the energy cost will be very high. So also we have to consider that the model used in the image generation. For example, if we want to use one AI-generated content model to generate, which is trained based on some city images to generate an image about a dog, the performance will be not that good. But if there is another model which is trained based on many animal images, it can generate an image about dog and cats in a very good way, but it cannot be used to generate an image about the nature. So in this case, how to select the different AI-generated content model is also very important. And here we consider there are many different edge servers, and on each server, AI-generated content model is deployed. And this kind of model have different ability in the image generation, and we should also consider the computing resources available on the edge server. If we allocate all the user tasks to one edge server, it may reach its limitation. So in this case, the service provider selection is a very significant problem in communication networks. After the server successfully done the image generation, it can download the finished test to the users. But in a real setting, the user may submit its task randomly, and we cannot predict what's the user's requirement, the arrival time, and also the computing resource cost. So what we can do is to collect the available information and try to obtain the selection solutions. And in this case, we can use the idea from the reinforcement learning. For example, the workload on different edge servers and the requirements from the users, the work requires like the number of denoising steps. This kind of environment information can be used as the information collected from the agent. So the reinforcement learning can get the network solution, and after we perform this kind of network solution in the environment, we will receive the feedback. So reinforcement learning can be used to solve this problem. But as we just explained, because the user have different requirements and the environment is very complex, the performance of reinforcement learning may be not that good. So in this case, we try to use the diffusion model to generate the image solution, the network solutions. Here we want to emphasize that the relationship of diffusion model and reinforcement learning, they are not like beating each other. Because for a problem, we can solve it in the reinforcement learning structure. But for diffusion model, the interaction with the environment, when the expert dataset is not available, the framework is also can be used by the reinforcement learning framework. For example, here is our proposed diffusion model-based SAC algorithm. Here the SAC is short for Sought Actor Critic. This is a famous reinforcement learning algorithm. First, we can take a look at this structure. We can see the diffusion model is used in the action generation. For example, the input is the observation, like the workload of the edge servers and the user requirements, and the output is the action, like we allocate this user task to which edge server. If we replace the diffusion model with a simple neural network, this framework is in fact just the framework of the SAC algorithm. So in this case, we can consider for a reinforcement learning algorithm, the actor network in fact play a same role of the diffusion model network. For the reinforcement learning algorithm, we can the input is also the observation from the environment, and the output is the actor's output, which is also the network solution. But with the help of the well-studied reinforcement learning algorithm, we can improve the performance of diffusion model. Like here, we replace the actor network with a diffusion model. With the strong learning ability from the diffusion model, it can model the environment in a better way and may achieve a higher performance compared with the reinforcement learning algorithm. And here, this is the output from the neural network, and we perform this kind of action in the environment, and we can get the observation. For example, the new workload information of the edge server and the quality of experience of the users. After collect this kind of state information and the reward information, we can perform the model training. In this case, we consider the actor network and the critical networks are working together. So for the actor network, now we use the diffusion model. The training loss function is to maximize the reward function. But if we directly use the reward function in the training of actor network, the training process is not that stable. So in this case, we can also create a create network. So the role of create network is to predict how much good the reward can be from the output of the actor network. So the create network and the actor network will be trained together. So for the create network with the training process, it can predict the value of reward function in a better way. And for the actor network, it can generate the action which can maximize the output of the create network. So with the help of this reinforcement learning structure and the strong learning ability of the diffusion model, we can achieve a very high performance for this problem. In these two figures, we show the comparison between our proposed diffusion model-based reinforcement learning algorithm with different kind of traditional reinforcement learning algorithms. As we can see, compared to these classical algorithms, the performance of the diffusion model-aided reinforcement learning is among the highest. Only the rainbow algorithm can achieve a higher converge speed in the beginning, but it failed to converge in a relatively good reward action. So in this case, we want to say the reinforcement learning can have different kind of structures, and many structures can be combined with the diffusion model design. Here, we also compared the reinforcement learning our proposed diffusion model-based reinforcement learning in the general benchmark tasks. For example, the robot control or the maze environment. As we can see, our proposed diffusion model-based algorithm can achieve a very high performance compared with these benchmarks. Okay, in the end of this lecture, we can give a brief summary. From this lecture, we give an introduction about the generative diffusion model and the wireless networking systems. And we can see the diffusion model have different requirements. For example, in the training process, we have to prepare a large amount of data, and the training and also the inference process will cost a higher computing power. But with the help of networking system, we can reconsider the training and the inference of diffusion model from the distributed way. For example, we can leverage the computing power in the edge devices and also the cloud central server. Also, the diffusion model can bring a higher user experience to the network users, and also the diffusion model can be regarded as an optimization tool for the communication network system optimization. So in the integration of diffusion model and the networking systems, in this lecture, we focus on the computing and the communication resources. But in fact, we can leverage more abilities of the networking system. For example, the wireless sensing or the caching mechanism. The generated content from the diffusion model can be cached in the network devices and reused to serve network users. And also, the sensing information from the edge devices can be used as the input of the diffusion model, so it will bring different problems compared to the text generation or the video generation. Okay, that's all for today's lecture. Thanks for listening.